Hello, everyone. My name is Ahmed Mohammed. I'm research scientist at SCOUS, and today I'll present to you our delay-aware compression control for distributed machine learning. The growth of recent machine learning applications have led to several things. First, we have larger data sets, and we have larger models to train on these large data sets. Training on large models on large data sets can take significant amount of time. As reported by recent OpenAI report, computation needs for ML has increased by 300,000x since 2012. And the computational gains of the latest generation devices cannot keep up with this. They are only capped at 2x. So one would wonder, how can I speed up my training? One can efficiently scale and parallelize the ML job by utilizing distributed set of nodes and their computational resources. However, the main bottleneck for distributed setting is the network or the communication. They are the major bottleneck for such setting. So many works have proposed compression to reduce the communication time. In a compressed communication training, workers would compute their local gradient, and before they exchange the gradient, they would compress the gradient. So they would have a compressed version of the gradient, which requires significantly less amount of time to communicate. And after this, they would decompress the gradient to obtain the gradient, aggregate, and update the model parameters. So compression can really reduce the volume and time. However, it introduces error, and therefore it may need more iterations to converge to the acceptable accuracy. So all existing work, or most of them, they assume that underlying network is static. So training is mainly conducted in dynamic environment. And this is reported by many recent work that latency and network speed varies a lot in many settings. So this is mainly due to the co-location or coexistence of different workloads in the same cluster. And this is the case in public cloud or mobile and WAN networks. So it's expected that you would have unpredictable runtime and resource underutilization for your ML jobs. And in this case, static compression cannot solve this problem. So our contribution in this work, we find that existing work on gradient compression arbitrarily set the compression knob via trial and error. And these preset knobs only work if network conditions do not change. So we try to answer these questions: how to find the right knob in a variable network condition, and how to exploit the trade-off between time and accuracy. Therefore, we designed DC2. DC2 is a plugin module that sits in between your ML toolkit and the communication library. And its purpose is to regulate the compression knob for your training. It does so by employing a submodule or delay monitor module, which collects network measurements. And these statistics of network on the network delays are fed into the compression control submodule, which adapts the compression ratio throughout the training. So we did an extensive experiments using DC2 with several types of controllers. And in this case, we show the results on training an LSTM on PTP dataset. And as we can see from the left-hand figure, we can see DC2 with the DA1 controller can achieve up to 41x speed up compared to the no compression baseline. And it can improve over the static 0.1 compressor by 5.3x. So in summary, statically configured compression isn't effective in dynamic networks. First, choosing the right compression ratio is actually difficult to begin with, and network variations can aggravate that. We designed DC2 as a first work to couple compression with the underlying network conditions, and its purpose is to control the compression ratio to maintain a constant iteration time. And also, DC2 suggests a new way to navigate the accuracy via training speed up trade-off. And from our evaluation result, we see that it can speed up the training in dynamic environment by 41x. DC2 also can be applied to most communication reduction methods with a knob. We applied it in our work to sparsification methods. However, it can be applied to quantization, where the gradients can be sent to with a lower bit width. And in this case, we can control the bit width. And it can be used with delayed gradient methods. And in this case, we can control the frequency of the gradients exchange. And it can be applied to many batch methods, and where we can control the batch size. Thank you. For any questions, please reach out to me.